Hi everyone, today we're going to be talking through an application of derivatives and tangent lines called linearizations and linear approximations. Now the thing I want us to have in mind right from the beginning is that when we talk about a linearization, all a linearization is a tangent line. So when we're writing linearizations, we're really going to be writing equations of tangent lines. When we're asked to write a linear approximation, really our goal there is to estimate the y value of a function using the tangent line. So if you keep in mind that this is really just about tangent lines, then it takes a lot of the confusion out of the topic. So here's kind of why we need linearizations. Let's say we have a function f of x that's x squared, and we're asked to find f of 2 and f of 2.1. Now we all know how to evaluate a function at this point. If I want to find f of 2, I'm going to substitute 2 for the x. I'm going to get 2 squared, and that's an easy question to answer. That's just 4. Now if I want to do f of 2.1, 2.1 squared is actually not a value that I have memorized. So I would need to go to my calculator for that. So in my calculator I would do 2.1 squared and I get 4.41. Now here's the big idea. For this second problem we needed a calculator to find this value. But what's going to happen is with our linear approximations here, this is going to give us a method to get a really close estimate of this answer without using a calculator. So that's kind of the big idea here, is how can we approximate values of functions without needing our calculators? So let's jump in here. Now, again, I said this is all based on tangent lines. So since a tangent line stays very close to the graph of the function when it is near the value at which it's tangent, and we'll talk a little more about what that means. So the tangent line is very close to the graph of the function when it is near the value at which it is tangent. We can use tangent lines to estimate function values. Okay, this process is called creating a linearization or using a linear approximation. Okay, so let's go ahead first and get a visual representation of this just so we know exactly what's happening here. So we're going to use that same question from the top of the page. So our function is x squared. Okay, and then we're going to be talking about the tangent line to f of x at x equals 2, and then we're going to be talking about the approximate value of f of 2.1. So first, let's go ahead and graph our function. Hopefully I can do this fairly neatly. Okay. All right, not great, but we get the idea. So there's f of x equals x squared. Now, I want to create the tangent line where f of x is equal to 2. So I'm going to create the tangent line to the curve kind of as best as I can here, just by kind of eyeballing it here. So let's see, draw it like this. All right, so there's my tangent line. So the idea here is if I want to approximate the value of the function f of 2.1, I know 2.1 is, let's say about here. So I would go up to my curve. And since that tangent line, well, first of all, since 2.1 is very close to the point of tangency, the value on that tangent line is going to be really close to the value of the actual function. Now, if I were to go further away, so if I were trying to use the tangent line to approximate f of 3, obviously that would not be as good of an approximation. So when we're talking about linearizations, we're going to be approximating values that are very close to the point of tangency. So that's the big idea here. We're using this red tangent line to approximate what's actually happening on our purple function in this case. So algebraically, let's take a look here. Now, we said that we're using linearizations, which are just tangent lines, to do these approximations. So the first thing is we have to write the equation of the tangent line to create that linearization. Now, to write an equation of tangent line, I need two things. I need a point, and I need a slope. Now the point, since my x value is 2, I know my y value is going to be 2 squared, which is 4. For my slope of the tangent, I know that's just the derivative of the function. So my derivative is 2x. So then I'm writing the tangent at x equals 2. So f prime of 2 is 2 times 2, which is equal to 4. And that's going to give me the slope of my tangent. So our first step is just to write the equation of the tangent line, which is going to be, let's see, y minus 4 equals 4 times x minus 2. Now, to get the linearization, all that is we're rearranging the equation to get y all by itself, because ultimately what we're trying to approximate is a y value. So I'm going to do that by adding 4 to both sides. So I'm going to do 4 plus 4 times x minus 2. And then I like to call this, instead of y, I'm going to call it L of x for linearization, is 4 plus 4 times x minus 2. So there's my linearization. Again, it's just a rearranged tangent line. So now if I want to approximate f of 2.1, I know that f of 2.1 is approximately L of 2.1, which means I'm just going to substitute 2.1 wherever I have x. So now this is equal to 4 plus 4 times 0.1. 0.1 times 4 is just 0.4. So now I know that f of 2.1 is approximately 4.4. Now, what I actually think is really cool and powerful about this is to see how close this gets us to the actual value. So when we used our calculator up here, the actual value was 4.41. And our approximation is 4.4. So we get really close. And again, the key here is that the function value that we're trying to estimate, the x value, is really close to that point of tangency. That's kind of the key to this whole thing. All right, let's go ahead and flip. We're going to look at another problem. In this case, we're given a table. So it says f is a function that's differentiable for all real numbers, so the derivative is defined at all points on the interval. It says the table gives the values of f and its derivative f prime, and then the second derivative of f has the property that f double prime of x is greater than 0 on the interval. All right, so we're going to write an equation of the line tangent to the graph of f at the point where x equals 1. So let's do that first. We're going to write our equation of our line tangent to the graph where x equals 1. So again, we know that we need a point, and we're going to need a slope. So we're doing this tangent to the graph of f. So I know that f of 1 is going to give me -4. So my point is going to be 1, -4. And I got that from f of 1 gives me a y value of -4. Now my slope, I need f prime of 1. So again, I'm going to go to my table, and f prime of 1 is going to give me a slope of 5. So my tangent line then is going to be y plus 4 equals 5 times x minus 1. Now, I know I'm using this tangent line to approximate a function value, so I'm going to go ahead and rearrange this. So y equals negative 4 plus 5 times x minus 1. So now I have my linearization. Negative 4 plus 5 times x minus 1. And this is what I'm going to use to approximate the value of f of 1.2. So use this line to approximate this function value. So I know f of 1.2 is approximately equal to L of 1.2, which is equal to negative 4 plus 5 times 1.2 minus 1. So if we simplify, we have negative 4 plus 5 times, that's going to be 0.2. Now, hopefully most of us would recognize we have negative 4 and 5 times 0.2 is just going to give us 1. So our function value is approximately negative 3. Now, in case you get tripped up with things like this, here's another way we could think about it. 0.2, right, is just equal to 2/10. Whoops, I'm off the page there. So if I have 5 times 2/10, that gives me 10/10 or 1. So again, if you don't see this right away, realize there's other strategies you can use to come up with this value. Because again, the idea is that we're coming up with these approximations with no calculator, so I wouldn't want you to think you could just go to your calculator and plug this in. Okay, so for right now, we're going to skip problem 2. We'll come back to that if we need another example in class. We're going to go on to page 15. We're going to talk about the accuracy of these estimations. So we can determine whether our linear approximations will be overestimates or underestimates by looking at the curvature of the function. And when we talk about that, we're really wondering about, are they curving up? Are they curving down? So this curvature is called the concavity. And it can be determined by examining the second derivative. Okay, so we have two things that could happen here. We could be concave up. That's when f double prime of x is greater than 0 or positive. If our function is curving up, right, we think of that like a cup. It could hold water. If I were to look at the tangent lines to that curve, so I'm just going to sketch in a few here, you would notice that those tangent lines all lie under the curve, so those estimates would be underestimates. Because if I were using that to estimate the value on the function itself, since they all lie below, that function value is going to be an underestimate. Now, concave down, on the other hand, is when our second derivative, f double prime of x is less than 0, or it's negative. Then our curve is opening down. We think of like a frown. In this case, if I were to sketch in my tangent lines, they're all going to lie above that curve, so any estimate we make would be an overestimate. And so we're going to use this in problems to analyze whether our estimates are over or underestimates without actually knowing the function value itself. So if we look at number 1 down here, right, this is a continuation of what we just did on this problem. So we found out that f of 1.2 is approximately negative 3. So that was the first part. Use this line to approximate the value of f of 1.2. And now what you'll oftentimes see is is the estimate an overestimate or an underestimate? And we know this has to do with the concavity of the function, which we can find out about that by looking at the second derivative. So if I go back to the problem, they told us that the second derivative of f has the property that f double prime of x is greater than 0. So since that's greater than 0, I know my function is opening up, which tells me that my tangent line is going to lie underneath, so I'm going to have an underestimate. So here's how we would respond to that question. We would say the estimate is an underestimate because, and we would just state what we know about the derivative, because f double prime of x is greater than 0. So this part is going to be extremely important. You will not get credit for your answer unless you're able to appropriately justify it using the second derivative. Okay, so we will stop there. Like I said, if we need to go through another example, we'll do that at the start of class, and then we'll go from there. Thanks.